I put up this slide to get started because my basic idea was we all we all work in computers, writing programs and applications and infrastructure and so on. But we all know that computers are very fast at processing. If you do a database lookup, geolocation, they are very fast at that. And there are certain things that humans are arguably good at. For the amount of processing power, now things are debatable. But the idea is the way computers do or process is different from the way humans process. And what we are doing here is we are actually teaching the computers the way the humans think. And I'm going to use the basic neural network example. And we're going to do this in Golang, right? So that's kind of the topic for today. Who am I? I'm a Observability Specialist. My name is Vinod Vydier. I work at Splunk. I also work in OpenTelemetry. Observability means collecting telemetry from lots of different places, infrastructure, applications, devices, and so on. So there's a large amount of data, and there is a lot of effort in now also using a lot of AI, which is, I didn't put the AI word because that suddenly puts everyone in hyper alert, right? Everyone is too interested into this. So I want to actually cover the topic from a historic perspective and how we actually go about building a neural network, right? Which is kind of the basic building block of all the hype that we have. So AI is has been talked about for a long time, starting from when computers first came around. The initial versions were, of course, just reasoning and basic rules and inference building, and people thought you can build on that and build human-like intelligence, which people realized very quickly that is not happening. It was hyped to an extent where a lot of people actually. So there was this. You must have seen the hype curve, right? This went into a deep trough where people realized, okay, this is something else, right? So there was a time period where AI has gone through a bunch of winters where no researcher wanted to do anything there. You wouldn't get any funding. No company wanted to do anything AI. So AI has actually gone through a bunch of these winters, and they've come back up with new ways of doing things. So the next wave was when there was some expert systems that had some human decision making. That's kind of the next wave. And then again, it kind of died down. And then there was this whole marketing thing that the Deep Blue and IBM had when there's computer beat a human, the best human in chess. And that was a watershed moment where people thought, okay, this is something that is really possible, right? Machines can actually be taught to beat the best chess player. The way they did back then was they had a bunch of good chess programmers, chess players and programmers, and they fed a lot of. So they created a chess engine, so to speak, with a bunch of humans. And Kasparov would play a move, and these guys would input that, and then they'd come back, churn out, and create a next move, right? So kind of a chat GPT of that era, but in some sense it was a chess engine. And actually it also gave rise to a lot of chess engines. If you're familiar with Stockfish, Stockfish is one of the most popular chess engines. And so even a cell phone chess game right now it's very hard for a human to beat that because the chess engines have got very good, and but it's actually not. The chess engines are not the neural network based. They are still a different kind of. So there was another watershed moment in 2017, which actually a lot of people don't talk about. I feel that 1997 to 2017 is a huge jump, where in 2017, actually just before that, 2016, the AlphaGo, there was a team of researchers that actually built something that beat the Go world champions. And in 2017, they built a similar neural network model where it would basically you teach the rules of the game, rules of chess, and then it would keep playing against itself. So kind of an unsupervised model where it kept playing and it got better and better, better and better. That the ELO ratings are now higher than the best player of chess. And it also had some supervised. It also learns all the previous games, and so it's very hard to beat. In a day, it actually got better than any human. So there are a few things that have happened where clearly there is something that you can actually build which can compete with the human pattern matching that is a human intelligence. There are a few more things that happened. This is of course a new era where generative AI is the third wave. But we won't get into that. That is the transformer-based architecture, which again in 2017 there was this attention is all you need paper that kind of started this new wave. But I would say the 2011, 12 when they had the AlexNet, that is kind of the beginning of some of these new way of building these models. So today we are all using some form of neural networks and AI behind the scenes, right? When we are on Zoom, you can turn on the auto caption, so you are doing the audio to text, through some sort of AI or a neural network behind the scenes. Same with if you have a picture on your phone, it automatically recognizes which person that picture. It associates a person. So today we will not do all of that. We will just do the basics. We will use the basic handwritten number recognition, which we have a lot of data from a long time. There is good folks at NIST. They created this data set where they have a whole bunch of. There's an interesting history behind NIST. They actually paid people to create these images, and they built 60,000. Let me actually show you the MNIST database. So it's a database of handwritten digits that is maintained by Google Labs, Microsoft Research, and also Jan LeCun. You might have heard of him because he's very, very active on Twitter these days. He has a beef with Elon Musk, and he's also the Meta Facebook AI chief. So these guys also maintain that MNIST database, and we are going to use that training set images, which is essentially a bunch of files that they have, which we'll use to train our network, and then it'll predict when you supply a network a file with a handwritten image of it. So I wrote down some numbers there. And this is any small kid, right, where they can recognize based on how that pattern is that it's number 4, and this is not very easy for computers, if you think about it. So that is what we are going to train the computer for, right? So that is the extent that we are going to do, and to do that we are going to use the same concept that our neural network, our human nervous system actually is built on, right? So there are synapses which connect these neurons, and we build something like that with the synapses are kind of weights that connect each of the neuron to another. So in the network you have a bunch of weights that are connecting to each other, and they come up with a output, right? So there's an activation function. We'll get into all of that, but this is what we're modeling this. And then we'll come out with a network. So we teach the network based on the input files that we have, right, from the MNIST database. And I will so from a high level we are inputting a file with an image, and it'll predict what that number is. That is kind of the high level functionality. And then we do some tweaking. We do keep updating the weights to get the right output, right? So that is what the training is, right? So to set the stage, we are using the MNIST database. We use those files to train our network, and then when we send one of the input files, it will predict what the right number is.
So in that example, the 784 represents the number of pixels in the image, right? And
Exactly.
So the ones that have it marked or
Exactly.
white, there'll be a 1 more or less, and when
Yep.
it's dark, it's a 0.
Yes, yes. So the one that is bright will be 1, and the one that is dark will be 0, and everything else in between. Yeah,
Okay.
you got it. So it's 784 because it's a 28 by 28 matrix in the MNIST database. Each of those input files in the training model is a file that has got 28 by 28. So, and actually to intuitively understand this, what we are really doing is we send this 784 inputs, right, with whichever. So in case of 9, you would have these MNIST file where it would light up those numbers or those neurons, and then each of the neurons is essentially like a binary, like 0 or 1 or number in between, right? Now, at every layer, you have a, based on these weights, you would have a thing that is lit up, which actually gives you a part of this number 9. So here, as you have multiple hidden layers, you have this loop, and there is a line here. So these two combine to make a 9, right? But this is kind of an intuitive understanding of this. Behind the scenes, every neuron is actually a number that is between 0 and 1. So that is an important thing to understand. This is kind of an intuitive understanding. What we are doing is we send a 784 array, okay, or you can say it's a vector, and then you send a matrix of weights, and then it comes out with another hidden layer. In this case, there are 2 hidden layers. In our example, in the Golang example, I'm just going to use 1 hidden layer because keep it simple. But essentially, what we are really doing is every one of these layers are small pieces, and then as you come to the output, you keep training based on these 784 input files, 60,000 of those, and then you keep training it so that you have the right weight, so that anytime you have another one of these, it will come back with the right number output. So we keep training this till you get a model that you can just send. So let me just. So finally, you what you want is something like this. You have an input. You go through the. I'll talk about this stuff. But this is what we really want, right? That is the output that, after you train. So in reality, what is happening is we assign some weights, how each of these neurons are connected to the next neuron, and we initially assign it based on what is, just as you said, right? What is lit up. But after that, the weights, it doesn't necessarily correspond to the hidden layer might have a different weight or a different number for each of those points in the array, right? Points in the matrix. So now what you do is, once you get a sum total of that entire weights, so there are 784 in the input layer, and then there is additional ones in the next hidden layer and so on, and then you pass it through. So you would get a number at the end of this, right? So actually this also, I need to explain this bias. So you have these weights that you're assigning based on what was initially lit up. Then you go through this layer, and the bias is something which is some way of saying that if you guys came to this meetup because you are interested in Golang, you're interested in this topic, you had a maybe not a very busy work day, and you had evening was free. So these are all factors. These are all variables or parameters. And then
I've got a question. So in training it, you're actually adjusting the weights until you get the right answer.
right answer.
And then you do that over and over until the weights become
stable value. Yeah, exactly. So there is a cost function. We'll talk about that. But yeah, that is exactly what we're doing. So these in this case, what I'm giving an example is there are a lot of factors that work in your head, right? When you're actually coming for a meetup, right? You have the interest level, you want to learn more about it. But if, let's say if there was a thunderstorm, you may not have showed up, right? So that is a big bias. If the weather is bad, we might have to cancel and so on. So that is a bias. So that is how you add up all these weights, and then you use a bias to come up with a meaningful activation input. And then if you look at this function, this is giving an output of between 1 and 0. So if you have so anytime you input this weights into it, so depending on whatever numbers that you're sending, you would always come back with the 0 to minus. Actually, yeah, in this case, you'll always have a value that is between 0 and 1. Actually, this is best illustrated on the whiteboard, or I can also show you this in a GeoGebra, right? So when you graph this function, you can see that, so for a very large value of x, you would have this becomes 0, so 1 by 1 is 1. For a negative value, it will be large value here, so it will become 0. Okay, so that is the sigmoid function. So whatever we calculate with the weights, we go through this, again it will come back with a number that is between 0 and 1. Okay, so that is what you pass to the next one. So we have these layers that are built up. So in this specific case, this example, these are the number of weights. So if you add up all this, these are the number of parameters or factors that are in there. So this is about 13,000, right? So you might have heard of ChatGPT with 175 billion parameters. Now this is yeah. Or what is the GPT 3.5 has got 175 billion, GPT 4 has got 1.7 trillion. These are all the, essentially they add up, a big number. They think it, so there is some amount of, you get impressed by that, right? But that is essentially what we are, talking about, right? And then based on these weights and bias, we send it through lots of training, like you said. And then you keep getting this function, so you get a number that you go through the sigmoid, and then you keep getting between 0 and 1, and you're also calculating the limit of this for each of these parameters. So this cost function that we are looking at, so as you keep coming down, you're trying to, so as you keep training it, you want to get the cost function to be the lowest. And that is what the model is eventually going to be, right? So I can let me actually yeah. This is a little So this is just one parameter. Okay. Now there are 13,000 parameters here, right? So this is with 2 parameters, it becomes a surface. So and each of them can actually have multiple minimums. So you're so when they say gradient descent is nothing but limit, you're doing a prime. So I would, and then based on the gradient, based on the limit, so you're actually coming down this slowly and getting into this weight, the cost function to be 0. And that is what eventually becomes your training function. And that is what eventually gives you the right. So I would actually also want to show you this part, because this is, I think, most easily understood with a sigmoid. If you guys remember some of your calculus, let me just move over here. So the sigmoid function that we looked at, right? So sigmoid function is right. So if you try to so limit of this function, right, which is which you can also say d by dx, right? You might remember this is so if you have x raised to n and you try to do a derivative of that, it would be n x raised to n minus 1. This you might have, you might remember this. So if you try to do this on this, you would get 1 minus e raised to minus x raised to minus 1, right? It goes up, and then so n times x raised to n minus 1, which is minus 2, and multiplied by, sorry, multiplied by, so the derivative of e raised to minus x is e raised to minus x times minus 1 d by minus 1. Okay, so this is n x raised to n minus 1 times derivative of this, which is the same, and derivative of minus x, which is minus 1. Okay, so the final thing is to minus 2 times e raised to minus x, which is equal to e raised to minus x divided by 1 minus e raised to minus x squared. So you can write this sigma, and if you can also write this as sigma times 1 minus sigma. So the reason this is this function is picked up is you can actually write derivatives just by multiplying these two values. So it makes it much faster to calculate, much faster to train. That's the only, so the whole point of this is you can do a derivative just by multiplying a sigma function with 1 minus sigma. And let me go back there. So all I was trying to show from this was, here is a sigma prime, right? So when I multiply or do a derivative of sigma, this is sigma prime. So this is GeoGebra calculator. So this was a sigma function. This becomes sigma prime. And then if I do a product of these two, they are actually exactly the same. Okay, so this is what actually we are going to be using in our. Let me just make sure that you. So if you look at the sigma, this product, it is also very close to the Gaussian, the normal distribution. So you can see that there is some, and Gaussian distribution is everywhere, right, in the real world. So that's all I wanted to show you, where, this is something that I already showed you. The exponential, the derivative of the exponential is also the same, right? So, yeah. So with that, I will now switch to the, so that is what we are really going to be using inside the program, right? So here, question? No, you good? Okay. So I have the MNIST database here. I have the train CSV file, and okay. So before we start, so everyone uses Python typically, right? And that's because Python has got a lot of good NumPy, which is a number, very good libraries for number manipulation, matrix multiplication, and so on. Go also has, believe it or not, has got GoNum. And you can use GoNum to do something very similar. It also has a lot of, it may be similar ergonomics, but yeah, there is a bunch of mathematical functions that you get out of that, right? So let's close that, and so I have this program which actually does three things. I'm going to show three things. One is to train the data, and I'm actually going to start in debug mode, so you can actually walk through. Okay, but before we do that, let me also start this, because the training will take a bit of time. So I'm going to do a train, and as we train that, we will step through the train program. So what we are really doing is, so first thing we are doing is, there's a MNIST train, right? So you are sending we are seeding it with a bunch of things, and so we are seeding a bunch of weights. We are going through the MNIST file, which is essentially 784 parameters in each of those lines. So these are all the, it's a large file with 60,000 training values, right? So I have these input images, okay, for every one of them. This is what I'm going to use to test it. But now when I go through this, let me actually step through this. So I go through 5 epochs. 5 times I'm actually going to read and retrain 5 times. So this is, you might have heard of overfitting and underfitting. So you just want to do enough. Don't have to, if you overfit, it becomes more of exactly the pattern that you taught it. It may not be able to adjust based on the input that you come in, right? So we're doing it for 5 times, but each of the time I'm reading it, and I'm actually, let me go to the next step. And I'm reading it and get out of this. And then I'm going to train it with the, I set up these weights and I start training this. I'm going to step into the training. And in training, I have, so before so each of this training network is a structure with inputs, hidden layer, and outputs. And then I have these weights that are essentially these matrix, which we initialized with some random numbers, right? And we're going to keep updating that. So as I keep going through this, so let me actually go through this some more. And so I'm also doing a dot between the, so when you do a matrix dot, what happens is if these 2 vectors are close to each other, then you come back with a lower number. So if the vector is exactly the same, it would actually have 2 vectors. When you have a dot product, if it's exactly the same, the dot product will be 0. If it is further away from it, it will be a larger number, right? So we are trying to find the number that is closest to 0, right? Sorry. and then we apply the sigmoid function to get to the next layer, right? And then we update the weights based on the sigmoid prime. So sigmoid prime is, sigmoid is the same thing that I wrote down, right? And then we have sigmoid prime, which is m times 1 minus m. So as I go through all of this, so now I keep training it for multiple times, and if I go through the entire thing, this is still going through that list of files. I would do this multiple times. So you're actually going forward, and then also updating the weights based on the prime that you're calculating, right? So that is what we were looking at here, where we keep coming back and updating the weights, right, based on the derivative. If it's a cost function is the lowest, then we update the weights. So I keep going through this multiple times, and then I would come back with a model that I have trained in about 4 minutes. Now, if I send a file, so let me send number 2, right? Number 2 looks like this. And if I send the number 2, I would come back, so number 2 looks like this, right? It comes back with the right prediction, because I've taught it. So I also have MNIST also has a test CSV that I can send it, and I can do a predict based on the predict. So based on the test files, I get an accuracy of 97.72. Okay, but I can do this for all the numbers that I have. I'm going to send all these input files, and I can see if it predicts correctly. So one becomes, it seems like it works perfectly fine. It is predicting fine. So let me actually show you what it's doing, right? So if I go through a file, so when I go through it's actually best to, so when I go through the predict function, what it does is the input data that it came in. So here this is 784, right, from the file, and then you start with the hidden weights, and then apply the sigmoid function, come back with the output, come out the final output, and so this is a matrix print. So it's just printing the input, the file, right, the matrix of the input file, and then it goes through that. Get out of this, and returns the best, which is prediction of 1, right? So I sent 1 here. So I sent the 1.png, and it came back with the 1. So this is something that you guys can play around with it, and I have some good. I actually took. There was an example that was out there, and I made some modifications, and there is very good descriptions on how this actually is built, right? So I would suggest you actually run through this, how the whole thing is built. But the basic idea is you are building this based on this CSV the MNIST training database, and then you're using that, and then you create this model, the hidden weights model and the output model, and then sending a new number file will give you the right output. I can actually go back and if there is any other things that is actually need more explanation, because I think this is the heart of the matter is to be able to iterate multiple times to get the cost function to the lowest, and that is what builds a model.
It does need to be iteration, right? Like Go is particularly good for running things concurrently.
Mhm.
I assume concurrency just actually don't even make sense in this case. It has to be like you're building these vectors, right? So,
Yeah.
So it has to be iterative.
Yeah, it has to be iterative. Yeah. But I mean, you can learn it parallelly and so on. That is definitely the ways you can optimize this. So the term backpropagation really means updating the weights. That's all it actually means. So based on what so you have a bunch of inputs, right? And you start with a weight matrix,
Right.
and then you come out with a output, and then you see the difference between the two.
Okay.
And then the cost function is how much that difference is, and you want to approach it. That is the gradient descent is nothing but taking derivatives and coming down to the lowest cost function. And to do that, you are updating the weights.
Okay.
So backpropagation is nothing but when you go forward. So when you predict, you are actually going forward through the model. When you're training, you go forward through the model, but then you keep updating the weights. So it's to make, so that is what the backpropagation is. So when you're training, you have to keep updating the weight so that you end up with getting the best output for all the input files that you have. Right? So right now, we have so much of data, right? So you have so much of text. So the transformer model is also similar, but so there is lots of different kinds of neural networks. There are different sigmoid function is not as efficient. There are lots of other functions that are even more efficient, and those are more advanced topics. But underlying stuff is basic math. There is not a whole lot of high school math is enough to really understand the math behind it. Yeah. So you are essentially trying to forward feed this and get the cost function to the lowest so that you can optimize this model.
Sure. So I mean, I can think of quite a few reasons that I would rather use other languages for this than over Go.
What? Give back that
for
piece
this
up.
particular use case. Is there anything about Go you find appealing for doing this?
I mean, Go is you end of the day you get a binary. You can as opposed to you don't need any other runtime on top, right? So that is one of the biggest advantages. And you have very tight binaries. You can much faster. You can do lots of parallel concurrency and so on. But yeah, you have to still keep iterating, right, to update the weights. Yeah.
I may just follow up. I generally find that the data science community is pretty useless on the core programming things. They have their domain and they tend to kind of stay there. So in general, I can't get my data scientists I work with to do anything that can't be put in the Jupyter notebook or something of that nature.
Yeah.
And so this is a compiled language. So is there some way I can use like the equivalent of like the Go run, sort of like debug run within Jupyter land, or is that just not going to happen?
There is no equivalent of Jupyter.
I guess you can do it in Python if you're a data scientist, right?
Yeah.
I think there are Jupyter plugins or
Yeah, but there are for different languages.
I know there's a thing for Java. I mean,
Yeah,
after Java 9, Java actually
Yeah.
introduced a REPL, kind of like, not particularly well-known fact. Java actually has a REPL, believe it or not. No one uses it, but it has one. But
No, for a lot of production load, people write this stuff in some another language, right? So most of the logic is built with Python. And Python itself uses a lot of C++ under the covers, right? For all the libraries that are written, they're all C++ libraries. So
Sure.
C and C++ libraries.
oh yeah, otherwise I wouldn't use Python either.
So it's I think more of ergonomics, right, for the data scientists. They want to use something that is easy. There's lots of libraries, and then eventually when it goes to production, you want to get something that is most optimal.
We got any other questions? All right.
No, but hopefully.
Otherwise, yeah, Vinod's going to keep walking off camera and everything.
yeah.
So, yeah. I tell you, it's hard to get good talent. It's just all over the place.
Yeah.
All right. Well, thank you.